Okay, it's Mr. Benson here with the next section of the practice exam. So we're looking at electronics and photonics. So starting off with the voltage divider question. So they kindly tell you it's a voltage divider, but you should recognize the pattern of it as well, as it's pretty classic here. So the first thing they're telling us is the voltage across the 1 kilo ohm resistor is measured to be 6 volts, and what is value X of the supply voltage there. Now there's a couple of ways you can think about this one. You could get out the voltage divider formula for a question like this. To be honest, I wouldn't if you could help it, because all you've got to think about here is that the total resistance here is 6 kilo ohms. That should be an equal sign. Oh, this is really getting tiresome. 6 kilo ohms, like that. Now that is 6 times as much as R2, which means that the input voltage is going to be 6 times as much as the output voltage, or the supply voltage as they're calling it, and so the answer to our question is 36 volts without having to do a lot of calculations. So then we can scroll down a bit further here. The voltage across the 1 kilo ohm resistor remains at 6 volts. What is the current through the 5 kilo ohm resistor? Give your answer in milliamperes. So all you've got to think about here is that we have a series circuit. So we've got 36 volts as our total voltage, and we've got 6 kilo ohms as our total resistance. So all we've got to think about here is that I through the whole circuit and also through the 5 kilo ohm resistor is just going to be V for the whole circuit over the half, R for the whole circuit, so it's 36, and the resistance for the whole circuit is 6,000 ohms, and so we end up with about 6 milliamps is our answer there. Okay, moving down to question C. So we have a supply voltage. So again, it's a now it's a similar looking question, but it's not a voltage divider because we have another resistor here. So that's going to change the nature of the circuit. We can't use the voltage divider formula. All we need to do is to think about this as just a year 11 circuits question. So they want the what's the current through the 5 kilo ohm resistor. So again, if it's going through the 5 kilo ohm resistor here, then this is the current for the whole circuit. So we've just got to think about the voltage, which is 18 volts, divided by the resistance for the whole circuit, and we will get our answer. So we scroll down a bit here. So the total resistance now, so it's 5 kilo ohms, so 5 by 10 to the 3 in series with, and then in parallel we've got 1 times 10 to the minus 3 inverted plus 3 times 10 to the minus 3, sorry, 10 to the not minus 3, 10 to the just 10 to the 3, my bad. So it is in fact just 10 to the 3 there, not 10 to the minus 3. Inverted, and remember to invert the whole lot. So this whole calculation can be done on your calculator in one step. Now remember that when we're doing times 10 to the minus 3, we use the EXP button, and we can type all that in really easily. So the total resistance there was 5750 ohms. So then our current is just the total voltage, 18 over 5750, and we get 3.1 times 10 to the minus 3, 3.1 times 10 to the minus 3 amps, but of course that will just be 3.1 milliamps because the milli is already in there. Okay, scrolling down to the next question. So this one confused me because they threw in some extra information, but it's a good question almost for that reason. They are adding in some extra information which will trick people who don't read it carefully. So students are investigating the voltage supplied by a photodiode. So that's actually telling you something already. The photodiode is going to be in a positive bias in your circuit. they shine light of varying intensity onto the collecting surfaces of the photodiode. So we've got some bits of equipment here, but where it's important is to actually read the description. Use all the items use the items available, not all, to draw up a circuit with a photodiode, switch, and variable resistor in a completed series circuit. Place the voltmeter in the circuit so that it measures the voltage across the photodiode, and the ammeter so that it measures the current through the variable resistor. So there's no battery in this, so they've given you an extra component that you don't actually need. So all you've got to think about really is, well, here's our wire, our photodiode. I won't bother draw. Oh yeah, I'll draw a little arrow in there. There's a photodiode. It's in series. Oh, I wish it wouldn't do that. It's in series with a variable resistor. Whoops, that's a thermistor that I've just drawn there. So the variable resistor has the little arrow on the end. Now there is a switch. Now normally when you're drawing a circuit, the switch should actually be across the top by convention. So I'm just going to put it there. Nothing on this side of the circuit. I really wish it wouldn't do that all the time. There's just wire up that side there, and wire across the, actually I need to go a little bit further, so the wire's going to go up there. It's going to come across the bottom, and we're going to have an ammeter here joined like that, and the last thing we need is the voltmeter, which needs to be there, measuring the resistance, measuring the voltage across the photodiode. So the main thing here is that the switch, the diode, and the resistor are in series. The order of them doesn't really matter. They could be in any order and it's still going to work as long as they're in forming one series circuit. The ammeter's got to be in series to measure the current, and the voltmeter has to be in parallel with the diode. So that's what you needed to do to get that one right. Okay, so we've got an IV characteristic of the photodiode. The switch is open. What is the reading on the voltmeter? What we need to think about there is the information that we've been given here. This one seemed easy when I first looked at it. Right, okay, and that's because it is. When the switch is open, there's no circuit, so there's no current flow. So that means that the voltmeter, it means that on our y-axis, we're at 0 here. So we read across and we get to this point here. So we find that our answer for B is going to be 1.3 volts because that corresponds with 0 current. The voltmeter measures 0 voltage across the photodiode. What is the reading on the ammeter? So this is basically the same question, but we're now reading from here upwards, and that is 3.6 milliamps is my answer there. Okay, now if the voltage across the photodiode is measured at 0.5 volts, what is the value of the variable resistor? So, got to think a little bit more about this one. Now the first thing that I'm going to think about here is, what does the graph tell me? Because we've been given a graph and we pretty much almost always need to use it if we've got one. When we've got 0.5 volts, I read up here and I see that I've got 2.8 milliamps. Now that's important because that's the current through the whole circuit. So I equals 2.8 milliamps. Now I know that my total voltage is 0.5 because there's nothing else in the circuit that can give me any potential. It's got to come from the photodiode. So V is 0.5 volts. And the only thing that can, or the only thing that's really resisting the flow of current here is the resistor, the variable resistor. So R equals V over I. I just have to sub in the values that I've just got from the previous answers and what have you. And this is 2.8 times 10 to the minus 3, and the answer that I get there is 180 ohms for my variable resistor. Okay, jumping on down to question 10. So we've got the IV characteristics of a diode. Now again, this is going to be important here. We're being given some information in the graph, and we'll almost certainly need to use it. Okay, a diode is placed in the circuit with a 6-volt battery, a 10 ohm resistor and a small light, shown without the diode. Draw the diode on the circuit so that the circuit will operate correctly. Now, what this means is that the diode has to be in a positive bias here. So if we put it in a negative bias, it would stop the current, because 6 volts is not high enough to overcome that. So we're going to draw it with a positive bias. So you could draw it there. Now you could draw it anywhere on the circuit as long as you've got the positive terminal of the power source here. So going around from positive to negative potential, your pointy end of your diode just needs to be pointing in that same direction as well. So we've got 2 marks there. It's pretty easy, 2 marks. Now if the current through the diode is 200 milliamps, what is the power dissipated by the light? Now when we have a look up at our graph here, what we see is that 200 milliamps is actually way off the scale of our graph. It's up here somewhere. Now that means that we have actually exceeded that threshold voltage for the diode here, which we can see is 1.2 volts. So that tells us that the potential drop across our diode is going to be 1.2 volts. Now let's have a think about what we know. So we know V diode equals 1.2 volts. So the power being dissipated by the light. Now the other thing we know is that the current through the circuit is 0.2 amps. 200 milliamps is the same as 0.2 amps. Now what we also know is that, or what we can also think about here is there's several ways you can think about this one. You could think about working out the voltage drops across each component in the circuit, and then you could work out P equals IV that way. The other way you could do it is you could think about the power in the whole circuit and then deduct the power from every other component in the circuit. Now that's the way I chose to do it, but it doesn't mean that that's the only way of doing it. So the way I thought about it was, okay, the total power in the circuit. Now I had a 6-volt battery, so P is IV. Now I for the whole circuit we know is 0.2, and V was 6 volts, so the total power in the circuit was 1.2 watts. Now then what we've got to do is deduct the power from other components. So the power for the diode, which I'll just call PD, is, now we know this is 1.2 volts was the potential drop across it, and it's 0.2 amps, so it's 0.2 times 1.2 equals 0.24 watts, so that's for the diode. Now the power for the resistor is, now I can use I squared R, so it's 0.2 squared times, now the resistor was 10 ohms, and we get 0.4 watts. And so then the power for the light, I'll just call PL, is going to be the total, which is 1.2 minus 0.24 for for the diode, minus 0.4 for the resistor, and we end up with 0.56 watts of power for the light. So you could either think about it in terms of the power and working out the difference, or you could think about it in terms of working out the voltage drops and then working out the power once you'd figured out the voltage drop across the light. Okay, moving on, we've got an amplifier question. So amplifier input-output characteristic. What to note about this one? We've got volts here and millivolts here. That will happen all the time, and you've got to think about that when you are doing the next thing, which is working out the gain. So remember that the gain is the gradient, the rise over the run. Now, if you look at this, we're going up 3 volts in this from here to here. Now I could do the whole linear region, but this will work fine. And we were going across 60, not 60 volts though, but 60 millivolts, which is times 10 to the minus 3. And we get 50 is our answer there. So our gain is 50. Moving on down, is the graph inverting or non-inverting? Now it is non-inverting. Explain your answer. Now I would say a positive gradient is part of that, but I would also say that a positive change in input gives a positive change in output. So it's not just that you know that it's a positive gradient, which is good, but it's actually that you can relate what that means from the input to the output voltages. Okay, the following graph shows the input voltage to the amplifier. On the output graph, carefully sketch a graph of the amplified output voltage. So, a couple of things to think about here. Firstly, we've established that it's a non-inverting amplifier, so it's going to output something that looks fairly similar. But where it is tricky here is that we're going to get some clipping, because if we look at our characteristic up here, we can see that our minimum values is negative 60 milliamps and our millivolts, sorry, and our maximum is 60. So when we wander on down here, we can see that at this point here and here and here and so on, we're going to get clipping occurring. Now, other than that, the shape of the graph will be much the same, and all we've got to do is look up at our characteristic again just to check where the where that clipping gets to, and it gets us to 3 volts of output. So then we can have a look back down at our output graph here. And when, sorry, I'm jumping around a little bit here, but you can see that when we are looking at the inputs, we can see roughly where they're going to go to on the outputs, but they'll be at the 3 volts. So we're going to have something like that. That'll come across a bit there. Then it should rise up, looking vaguely like a sine wave. Sorry, that was probably the worst thing I've ever drawn in my life. Then it will come back down. Whoops. Annoying annotations. Then it'll come back down to here like that. Then it goes back up, and well, that's awful. Right, so other than being hideously deformed, hopefully you get the idea here. So it still has much the same shape as the original sine wave, except that it's clipped when it gets to positive or negative 3 volts on this graph. Okay, moving on to now actually that'll do for electric circuits. I'll upload that one now, and I'll come back shortly with electric power.